Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
I have left some proofs incomplete last time. So, this continues more consequences. Of NNL. So, the proposition we were trying to prove last time about the height of prime ideals in the extension A to polynomial AX. So, Q is a prime ideal, so A is commutative ring and Q is a prime ideal in AX and P is the contraction of Q to A. Then we had three statements about the heights. Then one, height of Q mod Px. Px is the extension of P to the polynomial ring. This plus transcendent degree of the residue field at Q over residue field at P. This sum is 1. Two equalities, that height of Q equal to height P plus height of Q mod Px, and then if you use this equality 1, this becomes height P plus 1 minus transcendent degree of the residue field. And third one, height of Q equal to height P if Q is the extended ideal of P and otherwise it is height plus 1 if Q is not extended. And we have proved 1 and also this equality follows from 1. So, now we have to prove this 2 and this 3. We will first of all note that this 3 follows from 1 and 2. So, this 3 follows from 1 and 2. 3 follows from 1 and 2. So, we only have to prove only one equality, that is this one. But this equality also I will postpone because I need some more machinery from a local algebra, which I will postpone and I will assume for the time being and we will continue. So, one immediate corollary is if A is Noetherian, then the dimension of the polynomial ring in n variables is n more than the dimension of A, but Noetherian is very important. So, proof, we use induction on n. So, it is enough to prove that for one variable. enough to prove that dimension of a polynomial x is one more than the dimension. So, if you have a chain of prime ideals in A, so P0 contained in PR, this is a chain of length R in the spectrum of A. No, take in AX, and then therefore not P, but I will call it P primes. And when I contract to A, I will get PR. This is PR contained in P0, and we have checked that. So this means that height of P prime R is at least R, which is less equal to height PR, which is height PR plus 1. That is because of these formulas from here. See, height P is at least either equal to P or this. So it can at most increase by 1. So therefore, and this one is less equal to dimension of A plus 1. So therefore, one inequality is clear, dimension of AX is less equal to dimension A plus 1. For the converse, if I have a chain of prime ideals in A, P0 contained in PR in the spectrum, then the extended ones P0x containing not equal to P1x, these inclusions are also proper, because we have checked that if I take this and intersect back, you get back P's. So this is a chain in spec of AX. Therefore, and this I can extend it further by one more element, namely PR, ideal generated by PR and X, and this is proper. Therefore, from a length, the chain of length R in spectrum, I produce a chain of length R plus 1 in the spectrum AX. So that means the dimension of AX is at least R plus 1, but this R is arbitrary R, chain was arbitrary. So this is bigger equal to dimension A plus 1. So that was the equality. Okay, so the next theorem is also very important for the geometric reason. So this is called the dimension inequalities. So A, we will assume A is contained in B and they are integral domains. And assume A is Noetherian. And you take a prime ideal Q in B and contract it to A. P is the contraction. Then height of P height of Q, height of P plus the transcendent degree of the residue fields, residue field at Q over residue field at P, this is less equal to height of P plus transcendent degree of B over A. When you say B over A, that means this is the transcendent degree of the quotient field of B over quotient field of A. That is the definition of this transcendent degree. Yes. But let me check. On one side it is Q, so this is Q. This is Q. So I wanted to write some more statement there. Moreover, if B is a polynomial algebra, then the equality hold. Then the above inequality is equality. Is an inequality. Is an equality. Okay, so let us prove it. First, I will assume that B is actually a finite type K algebra, A algebra. So let us assume first. So proof. First, assume that B is an algebra of finite type. And then in this case I will prove the assertion by the number of algebra generators. So that is B is like this, A x1 to xn. These x1 to xn are the algebra generators of B over A, and we will prove the assertion by induction on n. For n equal to 0, there is nothing to prove, but anyway let us prove it for n equal to 1. So n equal to 1. So that is B generated as an algebra over A by one element. In such case, I will also keep saying that B is a cyclic A algebra. In this case, we will first prove the assertion, namely the inequality first, and then we will see when it is the equality. So to prove the inequality, I will assume by replacing A by A localized at P, we may assume that A is a local ring. A is a local ring, local with maximal ideal P. Because this inequality involves only P and Q, and therefore the bigger ideals are not playing any role, so I may localize at P. And in this case, the residue field Kp is now in the new setup. This is the residue field of A, that is K, which is A by P. And note that B is an integral domain and B is cyclic algebra. So, B is A polynomial x modulo some prime ideal. Let us call it somebody, let us call it R, where R is a prime ideal in Ax. Now, I will divide the further proof in two cases, namely this R is 0 or not 0. If R is 0 is the polynomial case and R is not 0 is non-polynomial case. So, the two cases we will consider. Case 1, R is 0, and case 2, R is not 0. All right. So, in case of R is 0, then B is actually P is a polynomial ring, and a transcendent degree of B over A then is 1, because when you say this, that is the quotient field at the quotient field level. So, the x is indeterminate. So, transcendent degree is precisely 1, and height of Q, we have just analyzed what happens in the earlier proposition. Height of P, the second inequality, this one I want to use. Height of Q is equal to, we are in precisely in the same setup. Height of Q is height P plus 1 minus the transcendent degree. So, this is equal to height of P plus 1 minus transcendent degree of KQ or KP. This is by earlier proposition. So, this actually proves what we want. So, what we want to prove is, here we wanted to prove this height of Q plus transcendent degree is less equal to height P plus transcendent degree, but height Q plus this transcendent degree is height P plus 1, and actually it proves the equality. That is what our assertion also says. Moreover, if it's a polynomial ring, then it is actually equality. So, this proves both the things, inequality which is equality. That is a moreover statement. Now, case 2, R is non-zero. That means it's a non-zero prime ideal. So, therefore, the transcendent degree of B over A has to be 0, because in this case the x is algebraic over the quotient field of A, because that precisely that R will contain non-zero polynomial and that will give a algebraic relation. So, write this, and this R is a prime ideal in B, which will be of the form Q, the given Q, we have given Q. So, Q is a prime ideal in B, Q is a prime ideal in B, but B is polynomial ring modulo this ideal R. So, therefore, R will look like some prime ideal in Q, capital Q mod R, where Q is a prime ideal actually in the polynomial ring. See, B is Ax is here, and B is a residue class ring of Ax by a non-zero ideal. This is B, this is surjective map here, and Q was given prime ideal here. So, this Q will come from some prime ideal here, that I am calling it capital Q. That simply means this Q, not R, Q looks like Q by R for some Q in the spectrum of Ax. And also note in this case KQ, residue field at Q and residue field at capital Q, they are same, because residue field means you go mod that and then take the quotient field, but when you go mod Q or go mod capital Q, they are the residue class rings are the same. So therefore it is the residue fields are same. Now I want to apply the case 1 to the ideal Q, which is ideal in the polynomial ring. So therefore by case 1 applied to Q, what we get is height of, in that case there is equality, height of Q plus transcendent degree of KQ, whether I write K capital Q or K small q, it is the same, KQ over KP, that is same as height P plus 1, that is by case 1. Because the other transcendent degree, this transcendent degree is 0. Okay. So once we have done this, now R is a non-zero prime ideal in R is a non-zero prime ideal, R is non-zero prime ideal in the integral domain. Ax, therefore height of Q, height of small q is smaller equal to height Q minus 1, because you can always extend the chain for Q by putting R in the beginning. So combining this with this, we can simply get, I will replace height Q by this smaller than. So therefore this is smaller equal to, so this we get the what we want. So this gives height P minus transcendent degree of KQ over KP, because the other transcendent degree is 0. Okay. So this proves the theorem for when B is a finitely generated A algebra. So this completes the proof if B is an A algebra of finite type.